In this presentation, we will discuss how to inject architectural resiliency of cellular organisms into autonomic computing using the DIME network architecture. We will discuss the resiliency, efficiency, and scaling in distributed computing systems. We will briefly recapitulate the Turing machine, the computation, and its limits. We will introduce a new computing model for autonomic computing, which includes self-identity, addresses self-reflection, and self-management. This is included in the DIME network architecture, which will provide a consistent monitoring and control of the computer and the computed, breaking some of the computation and its limits. We will show how we can use this architecture to inject architectural resiliency into distributed systems design. We will present a implementation of a self-managing LAMP stack without the need for virtual machines and hypervisors using the DIME network architecture. And we will also present a native operating system called Parallax-OS, which is specifically tailored to provide resiliency in many core and multi-core processors. According to George Dyson, there are two kinds of creation myths: those where life arises out of the mud and those where life falls from the sky. In this creation myth, according to him, the computers arose from the mud and the code fell from the sky. The concept of a Turing machine and the Church-Turing thesis have been the foundations of computer science for more than 70 years. The digital universe created by the Turing-John von Neumann legacy is expanding at a rate of 3 trillion transistors per second and 5 trillion bits of storage per second. How can one build a machine that performs 10 to the power of 9 different operations per second? The Turing von Neumann stored program control essentially used an instruction cycle to replace a man in the process of computing real numbers by a machine which is only capable of a finite number of conditions. The instruction cycle essentially comprised of an algorithm that is used in the instruction cycle: read, compute, change state, and write. However, much has changed since Turing compared a man in the process of computing real number to a machine which is only capable of finite number of conditions. The internet, high bandwidth communications, and multi-core, multi-threaded CPUs are all creating new opportunities to rethink the old computing paradigms. As is being emphasized in this conference, the many-core server is indeed causing an upheaval with its parallelism and performance. The 32-core and the 48-core microprocessor chips are causing a discontinuity in the IT industry. The sea change is not my word. According to Paul Cockshott and others, as described in this book, Computation and Its Limits, the key property of a general purpose computer is that it can be used to model any physical system of which the computer itself is not a part to an arbitrary degree of accuracy. However, their logical limits arise when we try to get them to model a part of the world that includes themselves. This is because of Gödel's prohibition of self-reflection in Turing machines. The evolution of computation can be examined with respect to three dimensions. The first dimension is the system resiliency, with which its reliability, availability, performance, and security can be measured. The second dimension is the scaling with the number of computing elements, and the third dimension is the efficiency with which the computing resources are utilized to effectively compute. The conventional computing originated from the von Neumann computing model and the Turing machine has provided very effective way to model physical systems and monitor them and control them, as long as the computer itself is not a part of that model, as Paul Cockshott pointed out. Now, in order to address the system resiliency and scaling and efficiency to include the computer and computing resources themselves, we have resorted to automation of various tasks involved in resource administration, such as CPU, memory, storage, network bandwidth administration. However, this has some limitations. Number one, because the self-reflection is prohibited, the layers of software that we have started developing to automate the resource administration has increased complexity with, for example, infrastructure as a service, platform as a service, software as a service. These layers all are added on top. In addition to that, there is a whole layer now that is added, which is based on the virtualizing the resources so that you can improve the resiliency. This is with the virtual machines and the hypervisor orchestration. On top of that, we have started adding application level management, and current operating systems cannot scale beyond a certain number of cores because of their design that originated from server-centric and limited narrow bandwidth origins. Even as many core processors are under development, there are already many core servers available today for commercial deployment that are using multi-core, dual and quad-core processors. However, current operating systems do not have visibility to all the cores, and therefore multiple OS images are deployed in the same container. These images communicate with each other using socket-based TCP/IP. End-to-end transaction management is provided through the orchestration of multiple management systems. So what we need is a new computing model that allows to model a part of the world that includes the computers themselves. So we need to go beyond Turing computing, and in this presentation we will attempt to present such a new computing model. On the other hand, there are examples where autonomy computing is the norm, not an exception. For example, a recursive computing model in the genome enables the beautiful unfolding of living organisms with self-configuration, self-monitoring, self-healing, self-optimization, and self-protection properties. In the telecommunication networks, the self-healing and self-management properties are made possible by the FCAPS fault configuration accounting performance and security management and the 800 call model using signaling channel. Human organizations have also developed elaborate processes to implement self-management. Even Turing himself proposed an oracle machine in 1939 to overcome the Turing machine limits. So, in this presentation, we will bring some of the common abstractions from these models to define a new computing model that will go beyond the Turing computing model and provide the features that will support autonomic computing, where you can model both the computer and the computed to address distributed systems management. It turns out that the key abstractions in all of these models are the following. Number one, you need to have self identity if you want self managing systems, and this self identity also has to be at various levels, like for example at a component level or a group level or at a global level. In addition, these structures all seem to support scale invariant structure processes, that is, description of stable patterns in these structures at any point of time, establishing a metastable equilibrium. In addition to that, the self management features are possible with two sets of different abstractions. Number one is all these systems have some form of fault configuration, accounting, performance and security management processes encapsulated at component level, group level and at a global level. In addition, all these systems have in common a signaling infrastructure that allows a control path to manage various tasks that are both processed by the computing elements and also the computers that are managing them. This signaling property actually provides, in the case of cellular biology, the 4 genetic transactions: the replication, repair, reconfiguration and recombination that are essential to provide the flexibility and control of the living organisms' self management properties. This picture shows the configuration of a computing system at any time. The system's entropy as a function of time depends on the number of CPUs, memory, bandwidth, storage capacity, storage throughput and their utilization. As the time evolves, as these computing resources are being utilized by external environment, the workload fluctuations, business priority changes and latency fluctuations cause the system to fluctuate around a equilibrium state in a metastable equilibrium. This picture shows, for example, response time as a function of time as the fluctuations in workloads, priorities and latencies change. If the fluctuations cause a disruption going above the maximum thresholds here, for example, then a phase change or a reconfiguration may occur so that the new equilibrium state then can be established and a new metastable equilibrium follows. This shows the Turing machine and its instruction cycle. Now, the Oracle machine introduced by Turing essentially interrupts the instruction cycle to consult an outside agent called the Oracle to proceed its evolution. Based on the response from the Oracle, the algorithm either stops, changes its state, or stops. This philosophy is used in designing the new computing model called the distributed intelligent managed element computing model, which provides the control architecture like an Oracle machine to set up and execute the algorithm as a Linux process. So, the Turing machine is the conventional Linux process, and it is set up and controlled by the control plane, which has non-von Neumann parallel threads managing the fault configuration, accounting, performance, and security management. The Turing machine now is essentially a Linux process that is loaded and executed after all of the resources are set up. The context and the constraints of the computation is known to the control plane, and it manages to monitor and control the Turing machine. Now, we can use this Turing machine to essentially monitor some temperature and based on its value control a fan. This process can be started and it can be stopped at any time, and it can be restarted any time. So, this provides a way to control the Linux processes, and the signaling layer in parallel allows a control plane where Oracle like behavior can be injected into the Turing machine. A network of such distributed intelligent managed elements can be used to provide a workflow implementation. This picture shows the recursive distributed computing engine nature of the DIME network architecture. Here is how the DIME network, which implements the safekeeping and self management of all of the DIME containers, essentially modeling the computer itself. And the DIME network is used to implement an external workflow that controls a group of fans and using the monitored temperature values of the thermometers. The policies are implemented at the node level and the group level and also at the global level. When a fault occurs, the policies will automatically switch over. So, you can see how we can implement auto scaling, performance optimization, failover, live migration, etc., etc. Here we show the implementation of self-repair and auto-scaling of an Apache server in a LAMP stack in DIME network without using hypervisors or virtual machines. The primary Apache is configured along with the DNS and the secondary and tertiary Apache servers. When the fault occurs on the primary, the secondary is used to replace the primary, and also at the same time the DNS is updated with the appropriate primary address. So, the service is continued without any interruption whatsoever. This picture shows the LAMP prototype where the response time is monitored as a function of the number of requests. As the number of requests increase, the response time also increases, and as we auto scale and add more dimes, the response time comes back under control. So, this shows how to do auto scaling and performance management in real time in the LAMP stack without using any hypervisors or virtual machines. Each Apache is treated here as a virtualized process that can be moved around. This picture shows 3 servers with Parallax-OS, each with 2 cores converted into dimes. A runtime orchestrator running in Linux provides the workflow execution across these servers. The proof of concept demonstrates creating a dime network, discovering the nodes and the cores, and creating dime applications with their management profiles and executing them. Various features such as I/O redirection, fault management, and live migration are also demonstrated in this demo. Here is a screenshot showing the Parallax-OS implementing auto failover of a program. There are 2 nodes here, and in one node each core is computing some function. When one of the nodes fails, the program is automatically switched over to the node 2 dime 1, which is a core, and the computation starts where it stopped before in the other computer. This is an attempt to model the dime computing using pi calculus. The computation and a meta model for computation that provides the context, constraints, and control of the computation are shown here. And the self management of dime and the dime network are modeled using a pi calculus recursive nested computing model. There have been other calls for new computing models. Here is Jack Copeland in the Alan Turing Centenary Conference public lecture talking about super Turing machines and hypercomputing. Peter Wegner has also called for new computing models during the past few years and has introduced his interacting machines. Roger Penrose in his Alan Turing Centenary Conference talked about a cautious oracle model and is also investigating into other mechanisms to cross the Turing computing barrier. While the Turing machine and von Neumann serial computing have served us well over the last 70 years. The hardware upheaval and the new bandwidth that is available among the processors in many core systems behooves us to investigate other computing models. This is where the real future of computing is. Here are two references. First one is a paper published by Rao McLean and Gianni Morana in the Turing Centenary Conference proceedings. The second one is a book, Designing a New Class of Distributed Systems, published by Springer in 2011